I'm Vivek. I'm going to share what we learned in terms of scaling our Kubernetes cluster for processing our data data workloads. So, and as part of today's discussion, I'll share like the challenges, the solutions. These are kind of the takeaways you could apply in your own clusters. And how did we scale for dynamic workloads that we are trying to process in Arcesium, right? And scale is something very close to an engineer's heart. Like whenever I look at reviewing the resumes of multiple developers, right, they would be conveying the scale in terms of either cost efficiency or latency improvements. And in fact, there was a time when if I sum up the cost reduction across 5-6 developers in a firm, right, it might even exceed the overall cost of the firm. But jokes apart, like the main theme is like developers want to work on those kind of projects where performance scaling are kind of core to their own heart. So, but the term scale means different things in different context, right? So let's understand like what we mean scale in terms of Arcesium's context first. So what we do at Arcesium, like so Arcesium is a fintech firm, right? And we build product for all post trading needs. So any investment firm in the world, they use Arcesium for computing their profit and loss, making sure things are reconciled against brokers. How many of you use Zerodha or any of the platforms? Oh, that's a very good crowd, yeah. So what you see in us as a dashboard in Zerodha, right? We do the similar thing, but for hedge funds and investment banks who trade in terms of millions and billions of dollars, okay? And we launched a newest product called Aquata, and that empowers the user to build their own data pipelines to process their data, okay? And this scaling challenge that we talk about is around how did we scale the Kubernetes cluster for Aquata, okay? Though we are talking about Aquata here, but it's the learnings from that is a takeaway for any of you who are going to run Kubernetes for their own data processing needs. So let's look at how a typical data processing flow will look like, okay? So you typically have data coming into your system. It's called as a ingress, right? And once it flows into, typically S3 is a kind of tooling they use. And data terms, it's called as a landing layer. So the data is coming to S3 and you connect your SQS to listen to all the object receive events on the S3. And whenever the event comes in, you want something to listen to it because you want to process the incoming data, right? So in the case of Aquata, we use a tool called Argo. Have any of you used it? Argo, that's good, okay. So not many hands, so I'll just give a very high level, okay. So Argo is an open source workflow orchestration tool, and it's built on native Kubernetes APIs itself. So it's not a separate application that's running, okay. And majorly it has two components. One is the events and the other is the workflow. The events is like a trigger manager. So based on the incoming event, it checks the dependencies and triggers the right workflow for processing that file. And Argo workflow is the workflow manager. So for each of the type of triggers, it needs to pick like what is the right workflow I have to use to process the incoming data, okay? And there could be even parallelism that is needed within the workflow itself. So the Argo workflows is a orchestration tool in simple terms. So let's dive a bit deeper, like what are the components within that? So within events, like you have three components, the controller pod and the S3 event source pod and your sensor pod, okay? And the event source pod listens to the messages from the SQS and it drains the queue from there, okay? And it puts that into a message bus like Kafka and post that the messages go to something called as a sensor pod, which makes sure like kind of filters, kind of manages the dependencies there. And when the right event is coming in, it will send a signal to the controller pod to then spin off the Kubernetes pods to do the actual processing, okay? So what are the challenges that we are facing? Like this seems like pretty simple, right? Like you have files coming in S3, it goes to SQS and it gets notified and you run the workloads. It's pretty simple. But what is the actual challenge? You have to understand like the context of the incoming data itself, right? So because Arcesium is trying to process the market transactions, right? It's very difficult to predict the volume of transactions that happen in a market. Like in a given day, it could be like a billion transactions that are happening, like, and depending on the news event, it'll suddenly jump to 10x or 20x. We don't know the count, okay? And a simple way to kind of solve for it is over provisioning your cluster, right? But that works if you have at least some steady state, right? In the case of market, you cannot predict like what is the trading volume in a given day. Leave a day, even for a given minute or hour, right? It's very difficult to predict what the volume is going to be. And being in fintech, there are many more constraints beyond that. So SLA adherence, that is kind of important. I believe a lot of you would have done SRE within your firms, right? Like how many of you have done SRE within your firms? Like you might have some form of observability. Hey, is my API taking more time or not, right? In the case of fintech also that's the case, except that these agreements lead to, any breach in agreements lead to losses. So it could be material loss for the clients, or it could be penalties that are enforced by the regulator itself because they're not following certain compliance regulations. And data integrity is crucial as well. Like we don't want to see a different number in the bank account. Like if it's higher, it's fine. But if it's lower, it's going to be a different case. And data misses can't be tolerated as well. Like if there are like a billion records coming in, we want all 1 billion to get processed. Not a single record can be missed, right? And data security is kind of a theme in any sector. Like with the increase in cyber threats, right? We want to make sure cyber security is coming early in the SDLC cycle, like what my previous speaker also spoke about. Now the challenge comes in when the first two combination is tied with the dynamic incoming workload itself. Because we are not able to predict it and you have to have a strict SLA, irrespective of the incoming volume, you have to process it in a shorter window. Like let's say the SLA is 10 minutes, right? For 1,000 records, also you have to finish it in 10 minutes. For 100 million, also you have to finish it in 10 minutes. So that's where the scaling challenge comes. Like, are we able to scale our processing to the extent where we are able to make it within the SLA itself, right? So that's the context around how we are trying to solve this challenge for like. So how do you solve for scale? Like, I believe like most of you would have solved for scale. Like it's not something new. Can you give some answers? Like I have some goodies who are very engaging. So just tell me some tool that you used for scaling your workloads. Autoscaler, yeah. Anything else? Serverless is a good one, yeah. Cool. So yeah. So these are good, very good tools actually. Like I'm really glad that this audience is at a different level. Like they are primarily knowledgeable. But if you try to search in Google, right, all you will get is, hey, move to Kubernetes, all your scaling problems will be solved, okay? But that is very far from true, okay? And so that's where we were as well. But we moved to Kubernetes long back, so we know what the challenges are, okay? And let's look at a typical scenario in Arcesium side, like how things look at. So we run close to 70K pods in a given day, and it's not like a steady state. The number of pods go up and down depending on incoming data. And the variance is close to 5K pods an hour, depending on the incoming volume. And the average pod size is like 8 GB and 2 core CPU, okay? And in terms of data volume, it's like close to 120 million records we process a day. And the variance is also very high. Like we said, like the market volume is varying a lot. And so what happens when we try to scale the system pretty quickly? So this is the flow that we saw earlier, right? So it adds pressure at multiple points within the cluster when we try to scale. So the first thing is your sensor pod wouldn't be able to keep up. Like there'll be too many messages coming in, right? And when it tries to message the controller pod, hey, do this processing, right? It wouldn't have enough resources to even start processing it. Things would start failing very rapidly. Okay. And what happens between the controller pod and your Kubernetes? Like again, the same thing happens. The Kubernetes APIs also start failing with different forms of error. Okay. And because Arcesium is hosted on the AWS cloud, we use EKS pretty core to our solution. Okay. And let's see what happens when the cluster tries to scale. Okay. So when the scale up happens, there might not be enough nodes on the Kubernetes cluster itself. Okay. Immediately your pod will go to a pending state. Okay. And the Kubernetes autoscaler would try to message to the AWS scaling scale group, says, hey, can you add a node to the cluster, because I'm not having any more nodes for scheduling my pod. And scheduling a node into the cluster is a costly operation. Costly not in terms of cost, but in terms of latency. Because what we want is to try to process all these data in a very short period, right? So that is a very latency sensitive operation. And the other thing is, once a pod is available, schedule becomes a problem. Like we need to start, Kubernetes has to create the pod on that particular node, and IP allocation is another step within the pod creation, which is pretty costly. And these are the steps which we found when we tried drilling deeper into trying to scale Kubernetes itself. And what are the scaling requirements required for processing the market workloads, right? In the case of Aquata, like the scale rate that we wanted was like we need close to 1,000 pods a minute. Okay, because the average size of the pod is around 8 GB and 2 core. What we wanted is actually 8 TB of memory and 3,000 cores to be scaled up in a minute. So that's the challenge that we were facing. Okay. So how do we try to make it work? Like from where will we get such amount of resources in a very short period? The main thing that how we tried investigating it is in terms of having good observability for the entire cluster and the kind of workflows that we have. So without observability tools being integrated with your cluster, it becomes very difficult to understand where the bottleneck is in the end-to-end flow. So once we got that, we tried simulating a similar setup in the cluster using Argo itself. So all of these are open source tools, so nothing related to Arcesium per se. And of course, since one way to do it is like you can throw cost at it. You can say, hey, I need 100 clusters, let's pre-provision it. It'll be costly for the firm, but more than that, we are engineers, right? So we don't want to solve all these challenges just by throwing money at it. These are like deep engineering challenges, and we want to try to solve by looking at it and trying to make it work way better. So once we tried inducing loader, right, we looked at each and every aspect of the points that we tried observing. And we are going to look at each and every choke point along the way, like what are the things that failed, right? So this was the first choke point. And what you see there was the error that we saw on our logs. So the sensor pod did not scale enough to read all the messages from the event bus. Okay, we saw that there was a huge queuing that is happening as soon as we try to scale up that much of messages. And what you see there is a client-side throttling. I believe like most of you would have configured throttler one way or the other in your APIs, right? So what is the primary objective of a throttling? Right. So it's more of a defensive check to make sure your pods don't go down. Like you know that your pod is going to take or going to process only 10 or 20 requests a second, and you want to make sure you don't receive like more than that, or it's not prone to DDoS because of that, right? So same is the case with the entire Kubernetes and the Argo ecosystem, right? These softwares are pretty well built, and each of these components, right, they have rate limits at various points. So this was the first rate limit that was hit. So what do you do? Like the rate limit has been hit. What are some of the proposals that you guys have? Increasing it? Okay. Anything else? Okay, root cause of the throttling, okay. Load balancer, okay. Okay. Yeah. So what we did was like, yeah, identifying like what was the root cause of the throttle itself. So they have set up, I mean, most of these projects, right, they have pragmatic throttles. Like they work for 80% of the cases. So these throttles are not like magic numbers. They have been calculated based on certain limits that they have been provisioned for or designed for, right? So we went through that and we identified that, hey, increasing the throttling is not going to be sufficient, like, because it's going to bring down the system even further, because we are trying to remove a defensive check, right? You also need to provision enough capacity to make sure the increased number is capable of handling the load, right? So that's what we did. Like, we changed the QPS for the sensor from 100 and the burst rate to 200. Okay. Along with that, we also made sure we provision enough resources and scale limits to ensure this particular QPS can be catered for. Okay. So that removed the first choke point, right? But the thing is, performance engineering in a distributed network like this is like peeling onions. Have you guys peeled onions? Yeah. So each time you peel, right, you get one more layer, right? It's not like you solve for one thing and you're done. So this was the first choke point we hit, but the moment we solved for it, we hit the second one. And the second one was at the controller pod. And the controller, what it was trying to do was trying to see, hey, I want to create more and more pods, but I'm not able to, right? So this is the error that comes from the controller pod logs. And we could see this as well in our Datadog dashboards. So we use Datadog for monitoring within Arcesium, and we could easily observe that, hey, there are too many pending messages that is waiting in the controller pod itself. So it's a similar kind of a story. Like, we increase the throttle for the controller as well, but doing so is pretty dangerous. Like, you have to ensure that you are actually provisioning resources and making sure it is able to sustain that particular throttle limit. So we increase the resource as well as the thread count. So these are kind of internal to the Argo itself. So we tried increasing these two metric and made sure that it is capable of handling this 256 QPS. And suppose that we hit the next bottleneck. Now, Kubernetes APIs were not able to scale. Like, Kubernetes APIs also have a good amount of throttling within it. Like, for folks who have not used Argo, this would be like a direct messages you have seen whenever you try to scale your Kubernetes cluster. Like, it would say, hey, I'm not able to allocate the IP address, right? Like, if you have used the AWS CNI plugin, right, there are a limited number of IPs that can be assigned for a given node type. And the kind of architecture that we have built, we wanted namespace to be at a pod level. So we didn't use AWS CNI, and we couldn't use the warm pool as well that was available in the AWS CNI. So what we did here was we moved to a tool called Cilium. Like, have any of you used Cilium or heard about it? So Cilium is another implementation of the CNI, but it does much more than that. Like, you will be able to do network policy, could be directly put on top of it. A lot of things which are kind of tricky in the Kubernetes networking is handled by the Cilium open source tool itself, right? Oh, sorry, it's not open source, it's like kind of a freemium model. So once we did that, the Kubernetes side or the IP allocation was something that we could get ahead with. Now, the K-pods were able to spin up at much faster rate, right? And besides this, we also did some additional improvements. So one was around the noisy neighbor problem. Like, what if there are two different clients who try to kind of bombard the system with too much of data? Like, how do you ensure there is a parity between these two clients in terms of scaling up, right? So we had to tackle that in the throttler itself, and this throttler was within the Argo workflows. So the way we try to do it is, like, for each client, we give a specific quota, and we make sure the quota increases the same pace as a scale up across all the namespaces. And how many of you have heard about thundering herd problem? Okay, cool. So I'll tell you what it is. So let's say an API goes down, right? You would have added retries in the consumer side. How many of you have done that? Retries? Yeah. Because there are a lot of frameworks to do these retries in automated way, right? But the moment the API comes back online, right, all of those retries are going to hit the API, right? That is what is called as a thundering herd problem. Okay. Now, this is what exactly happens when a new pod or new node gets added to the cluster. Now, all the pending queues that we have so far will try to create a new node on the create new pod on the node that got added. Now, the node would have limited resources, but all the requests that came in will try to create a pod. Now, this is what would result in a thundering herd problem, similar to how an API comes up and all the retries are going to mess up the system again. So this is where we do exponential delay and such strategies, right? So a similar kind of strategy we followed to ensure that as soon as a node is added, we don't kind of add too many things, but rather based on the number of nodes that got added, we'll try to give quota to the incoming queues as well across namespaces. So these two is kind of are challenges for people who do multi-tenant computing in their Kubernetes clusters. So with all these, right, this is how it looked like. So in the beginning, we were kind of peaking at 2.5K pods at a given time, despite having enough, further data to process. And the end-to-end was taking like close to hour and a half. Okay. And after these changes, right, we were able to kind of scale up from 0 to like close to 9K or 10K pods with the changes that we have done so far. And the processing rate also increased a lot. Like we were now able to kind of process things in a much shorter window as well. And let's look at like what are the kind of key takeaways that we have, which you could go back and try to implement in your own cluster, right? So the first one is like observability is a must. Like without observability, you are just trying to like just aim and shoot without looking at the target, right? So observability is a must. Make sure like you have your Prometheus metrics turned on the cluster. Make sure like you have end-to-end tracing as well. Second thing is like Kubernetes has rate limits at multiple layers, right? The kind of error messages that it throws out is very meaningful, and don't increase the rate limits like as and when you hit them. Rather try to analyze like what leads to those rate limits and provision for like an increased scale of processing for each of the layers. And image caching is something that helps as part of the K-pod startup itself. So beyond the IP allocation, right? If you have the images cached in that node, it helps in terms of scaling up more nodes in the pods in the same node. And in terms of Argo workflows, like make sure that you measure the limits at each of these stages, like events or workflows, and try to scale them at individual pieces. And Argo is a software where you can extend it easily. Like you don't have to go into the source code for changing it. Like they have enough interfaces to ensure you can create your own throttler, your own rate limits. So do that rather than trying to modify it overall. So these, I would say, are the key takeaways in terms of how we scale our Kubernetes cluster. So here are the key members who worked on it. And we have Rini with us as well, like she's over here, and we'll be there in the booth, which is set right opposite the main hall. So yeah, that's about it.